Good day to all of you. In today's lecture, we will look at selected problems in power conversion circuits. In the past 3 or 4 lectures, we had been looking at the steady state analysis of power conversion circuits by making certain assumptions of ideal operation of the switches, ideal performance of all the energy storage elements, and with these ideal conditions, we developed the principle of volt second balance on inductors and charge balance on capacitors, and using these basic principles under ideal operating conditions, we found out how these power conversion circuits were performing. We found out what is the voltage conversion ratio of different power converters. If certain input voltage Vg is given to a power conversion circuit, which is operating with switches, operating with certain duty ratios, then how this input voltage Vg got converted to some other voltage and delivered to the load as V out, output voltage. The ratio of output voltage to input voltage is one of the important parameters in the power conversion circuits, and similarly, if certain current is drawn from a power converter at the output, how does it reflect on the input source of the power converter circuit? Ig, the source current, divided by I naught or the output current. We said V naught by Vg is one of the important conversion factors in a power converter. It is called the forward voltage conversion ratio, and similarly Ig by I naught, which is called the inverse current conversion ratio. We saw how these quantities can be evaluated based on the idealized operating conditions, and we invoked the principle of volt second balance and charge balance on the electromagnetic energy storage element inductors and electrostatic energy storage element capacitors. So, in this session today, we will practice how we will apply these principles to find out the different conversion ratios of power converters. And we also saw that under steady state, these converters also were not converting the voltage perfectly to DC, but there was some over ripple voltage, an AC ripple present on the capacitor voltages, and similarly AC ripple present on the inductor currents. And this ripple calculations also is one of the important performance index of the power converters. So, in today's session, we will try to take several power converter circuits and try to apply the principle of volt second balance and charge balance and evaluate under ideal conditions what is the voltage conversion ratio, what is the current conversion ratio. Similarly, what are these voltage ripple quantities, current ripple quantities, or alternately if these ripple quantities are specified, what is the value of inductors and capacitors to be used in a circuit, and so on. This is the problem set which we would like to see first. You will notice that there is a source which is Vg, and to the load, a resistive load, a voltage of V naught is delivered by this power conversion circuit. The power conversion circuit has an active switch S and several passive switches D1, D2 and D3. And during the on time of a switching cycle, which is T on, the switch S and the switch D2 are on. And during the off time of a switching cycle, the diode D1 and the diode D3 are on. So, this is the operating condition, and it has 2 energy storage inductors L1 and L2 and 2 energy storage capacitors C1 and C2. The inductor currents may be called IL1 and IL2 under steady state, and the capacitor voltages may be Vc1 and Vc2 under steady state. So, our concern now is to analyze this circuit using the volt-second balance principle and the charge balance principle and evaluate the power conversion ratio and so on. So, we can see that this circuit operates in two different sub cycles. We will call this as T on and T off. In every cycle, there is one interval known as T on and one interval known as T off, and the total cycle T on plus T off is equal to Ts, which is one cycle time, and this ratio of T on by Ts is normally defined as the duty ratio of the converter D. So, during the on time, D2 is on and S is on. Power now is flowing from the source to the load. Inductor is L1 having a current of I1 and L2 having a current of I2. And this capacitor Vc1 has a voltage of capacitor C1 has a voltage of Vc1 and capacitor C2 has a voltage of Vc2 under steady state condition. Now, during the off time, the switch S is off and the diode D2 is off, and instead D1 and D3 are on. The circuit conditions now are L1, C1, D1 form a closed path for the current, D3, L2, Vc2 form a closed path for the current. Now, in this particular situation, we are interested in finding out what is the relationship between Vc1 and Vg, that is, what is the conversion ratio Vc1 to Vg under steady state, and on the output side, what is the conversion ratio Vc2 by Vc1 under steady state. Now, these quantities can be evaluated by applying the principle of volt-second balance on each of the inductors L1 and L2 one by one. So, we might see that on L1, on the inductor L1, it is possible to apply the volt-second balance. For example, the L1 has a voltage of Vg on this side and Vc1 on this side during the on time, and during the off time, the voltage is simply plus minus Vc1. So, we might say volt-second balance on L1 as Vg minus Vc1 multiplied by T on plus, in the off time it has only Vc1, but with minus on this side and plus on that side, into T off, this sum is equal to 0. Right. So, from this it is possible to find out the condition that Vc1 into T on plus T off is Ts is equal to Vg into T on, or we say that Vc1 is D times Vg. So, this is the first relationship. When we apply volt-second balance on L1, we find the condition that the capacitor voltage Vc1 is now D times Vg. Right. Under steady state, this should be the relationship of voltage conversion that takes place in the first stage of the power conversion, Vg to Vc1, and that is what we see here. Right. Now, we can find out again, if we apply volt-second balance in L2, we will be able to find out the relationship from Vc1 to Vc2. For example, during the T on time, the voltage on L1 is Vc1 on the left hand side and Vc2 on the right hand side multiplied by T on. So, that is the volt-second during the on time, plus during the off time, this end is 0, this end is Vc2. So, we might say that minus Vc2 into T off, and if both these are over one cycle, if this is added and equated to 0, then we find that Vc1 into T on is equal to Vc2 into Ts, or Vc2 is equal to D times Vc1. So, this is the second relationship by applying the volt second balance on L2. Now, we find that the voltage conversion ratio from Vc1 to Vc2 is D, and from Vg to Vc1 is D, or we can say that Vc2, which is the output voltage which is same as V naught, is D square times Vg. So, this is really a two-stage buck converter. There is one stage of D times Vg in the first L and C, and there is another stage of D times Vc1 between L2 and C2, and effectively the output voltage is D square times Vg. This particular converter is also called a quadratic converter, because the output voltage is square times square of the duty ratio times the input voltage. This is a quadratic converter because output voltage is a square function of the duty ratio, unlike the simple buck converter. So, we might say that in this converter our V naught is D square times Vg. So, this is the first operating condition on the power converter. What is the forward power conversion ratio? Now, in this, supposing if Vg is 100 volts and duty ratio is 0.6, we can say that the output voltage V naught will be D square times input. D square is 0.6 into 0.6, which is 0.36. 0.36 into 100 is 36 volts. So, in this particular example, when the input voltage is 100 volts, duty ratio is 0.6, the output voltage ideally will be 36, and with the resistance of 12 ohms, the output current will be 3 amperes. Right. So, we have a power converter now which takes in 100 volts at the input, operates at a duty ratio of 0.6, produces 36 volts ideally at the output, and delivers on a 12 ohm resistor 3 amperes of current. And if we further specify that this converter operates with a duty ratio with a switching period of 20 microsecond, it is possible for us to calculate what will be the required value of L1, L2, C1, C2 and so on. So, with the specified period of switching at 20 microsecond, let us find out what will be the required value of L1, what will be the required value of L2 and so on. We have assumed that all the switches are ideal. It means there are no losses in the converter. If that is so, then we might also say that the input power is the same as the output power. So, we might say that 100 times Ig is equal to 36 times 3 amperes. The output power is V into I, 36 into 3. Input power is Vg into Ig. So, from this we can say that the input current Ig, average current will be 36 into 3 divided by 100, and that is 1.08 amperes. So, what we might say is that the average current drawn from this converter is 1.08 amperes. And here one can see at the inductor the output current 3 amperes also has to come from the inductor L2, because C2 does not supply any DC current. So, the DC current on L2 will be the same as the output current. So, this will be 3 amperes. And then this 3 amperes is coming out of this branch for a duration of duty ratio 0.6. So, we might say that the average current of L1 will be this 3 multiplied by this 0.6, which is 1.8 amperes. So, we might say that IL2 is 3 amperes, same as I naught, and IL1 is 3 amperes into 0.6, which is 1.8 amperes, and Ig is 0.6 into 1.8, which is 1.08 amperes. 0.6 multiplied by 1.8 is 1.08 amperes, which is the same as this current. So, by the assumption of volt second balance and ampere second balance on the capacitors, we have now managed to find out all the average currents in the inductors and the voltage ratios. For 100 volt input, we get a 36 volts at this point, and this capacitor will be 60 volts. 0.6 into 100 is the first stage conversion. So, VC1 has a voltage of 60 volts, VC2 has a voltage of 36 volts, input voltage is 100, output current is 3 amperes, the first inductor current is 3 amperes, the input inductor current is 1.8 amperes, and input average current is 1.08 amperes. All these we are able to do by invoking the condition of volt second balance on the inductor and the ampere second balance on the capacitor. Now, let us look at the conditions to find out what will be L1. For example, we had seen that IL1 in any cycle where duty ratio is 0.6 times Ts, off time is 0.4 times Ts, and the inductor has an average current of 3 amperes. So, we know that during the on time the inductor current increases, and during the off time inductor current decreases. So, this is our steady state inductor current, and inductor has a ripple current of certain value. So, if we assume this delta IL by IL as 10%, 0.1, then we can say that delta IL is 0.3 amperes, because IL is 3 amperes, delta IL will be 0.3 amperes. And this off period is when the inductor has a di by dt of output voltage V naught divided by L2, 36 by L2, and this off duration is 20 microsecond multiplied by 0.4, which is 8 microsecond. So, in this triangle, the slope is 36 by L2, duration is 8 microsecond, and this di by dt into time is delta I, which is 0.3 amperes. So, from this one can say L2 will be 36 into 8 micro divided by 0.3. So, this would be 120, 36 by 0.3 is 120. So, this would be 960 microhenry. Our L2, that is the secondary, the output side inductor current L2 will have a value of 960 microhenry. Okay. And this is obtained by finding out what is the di by dt during the off time, what is the duration of the off time, and the assumed ripple current, which is 10% of the total current. In the same way, it is possible for us to find out the ripple current on the input side inductor. We know that the input side inductor also follows a similar kind of on time, off time, current is increasing and decreasing, and this current on the input side inductor is 1.8 amperes. So, we might put a condition that this delta IL is 10% of that, which is 0.18 amperes. If delta IL is 0.18 amperes, then during the off time the inductor faces a voltage of 60 volts and inductor value is L1, 60 volts divided by L1, and duration is 8 microsecond. So, we might say that 60 by L1 into 8 micro is equal to 0.18. So, from this L1 can be calculated to be 60 into 0.8, 60 into 8 divided by 0.18, 60 which is 2.67 millihenry. Now, the same principle was applied. We found out what is the di by dt during the off time, what is the voltage across the inductor, and the di by dt is V by L, and during the off period this inductor is losing that voltage. So, the total current ripple is taken to be 10% of the average current, and by finding out the relationship between these two, V by L into T is equal to delta I, we are able to find out what is L1. In this particular example, we find that L1 is 2.67 millihenry and L2 second inductance is 960 microhenry. Okay. The same principles of the circuit equations L di by dt equal to V is what is used, and during off time the L di by dt is the same as output voltage, and from that equation we are able to find out what is the relationship between L and delta I, and by forcing delta I to be 10% of the total current, the inductor average current, we are able to evaluate the value of inductor. By applying these principles, we have found out what is the value of N and what is the value of L2. So, if we go back again to the problem set as we had given, we are able to find out what is the voltage conversion ratio, and from the input to the output, what are the currents in the various inductors, what are the voltages in the various capacitors. Then by forcing the condition of current ripple to be 10%, we are able to also find out what could be the value of the required inductance in the converter. As a next measure, what we will do is, by forcing the voltage ripple on the capacitor to be certain percentage, we can find out what is the value of the capacitor C2 and what is the value of the capacitor C1. Let us come back again to the circuit condition. We have the inductor L2, capacitor C2, and here we are drawing a current of 3 amperes. So, we see that the inductor current is varying between minimum and maximum, and this ripple current is 0.3 amperes and the average current is 3 amperes. Right. So, in this particular example, if the output current is exactly 3 amperes, then what we see here, the current above the DC current is the current going into the capacitor, and what we see here, the current below the DC current, output current, is the current coming out of the capacitor. So, if we know what is the current going into the capacitor or what is the current coming out of the capacitor, it is possible to find out what will be delta Vc, because this is the current which is discharging from the capacitor and this is the current which is charging from the capacitor. And if we find out the charge into the capacitor, which is nothing but delta I by 2, which is the height of this rectangle, into Ts by 2, which is the base of this triangle, into 1 by 2, this is the total quantity of charge, that divided by C2 is delta V. So, I might put a condition that delta V is 1% of the output voltage, which is 0.36 volts. Output voltage is 36 volts, 1% of that 36 volts is 0.36 volts. Now, this equation, all the quantities are known except C2. We know that delta I is 0.3, Ts is 20 micro. So, it is possible now to write C2 as 8 into delta V in the denominator, and delta I is 0.3 and Ts is 20 micro. So, if this is simplified and delta V is 0.36, so if this is simplified, 0.3 20 micro divided by 8 into 0.36, which is 0.3 into 20 micro divided by 8 divided by 0.36. So, that is 2 microfarad. So, what I need at the output of the converter is a capacitor C2, which has a value of 2 microfarad. So, that the output ripple voltage is 0.36 volts. So, what we have used in this relationship, in this particular evaluation, we have found out C2. In this evaluation is the amount of charge coming into the capacitor during the on time and the amount of charge going out of the capacitor during the off time. And we take any one of them, the charging current as the top triangle or the discharging current, which is the bottom triangle, find out the total charge that is either going into the capacitor or coming out of the capacitor, use the relationship that Q by C is V for this application, and from that, if we know what is delta V and the charge that is going into the capacitor, we are able to evaluate the value of the output capacitance C2. So, in this particular example, we need a capacitance C2 of 2 microfarad. If we further go in, it is possible to find out next C1 capacitance also. This is a little more different in the sense, if you see the equivalent circuit, this is C1, which has a voltage of 60 volts. So, we might say that we would tolerate a voltage ripple of 1%, which is 0.6 volts. Now, in this circuit, we know that this capacitor has on this side an inductor which is giving a continuous current of 1.8 amperes. The continuous current coming on the input side inductor is 1.8 amperes. But on this side, we know that there is a switch which turns on with a duty ratio of 0.6 and the current of 3 amperes. This is the equivalent circuit seen from the node of that capacitor. So, what we see now is that this 0.6 into 3 is the average current going out here. That average current is the same as the average inductor current. So, that there is no net average current in C1. But during the time this inductor is, this switch is open, where the inductor current is freewheeling, this entire 1.8 amperes is flowing into the capacitor C1. So, you might say that the charge going into C1 is 1.8 amperes multiplied by the off time. Off time is 0.4 into 20 microsecond, which is 8 microsecond. On time of this is 0.6 into 10 microsecond and 20 microsecond. Off time is this. So, the amount of charge going into the capacitor is 1.8 into 8 microsecond. This divided by C1 is the ripple voltage, and ripple voltage is 0.6 volts. So, now from this C1 can be calculated to be 1.8 into 8 micro divided by 0.6, that is 3 into 8, 24 microfarad. So, you can see that this is 1.8 into 8 divided by 0.6, which is 24 microfarad. So, in this particular example, if we wish to keep the voltage ripple at 0.6 volts for an average voltage of 60 volts on the capacitor C1, the charging current into the capacitor is 1.8 amperes into 8 microsecond, and the capacitance value is C1, and the ripple voltage is 0.6 volts, which is 1% of 60 volts. By equating this relationship, I can find out the value of C1, and that is 24 microfarad. So, in this particular example, now we can put all these things together and say that our V0 is 36 volts, I0 is 3 amperes, IL2 is 3 amperes, IL1 is 1.8 amperes, VC1 is 60 volts, VC2 is same as V0, which is 36 volts, and then L1 is, how much did we find? L1 is 2.67 millihenry, and L2 is 960 microhenry, then C2 is 2 microfarad, and C1 is 24 microfarad. And this is with the condition that the current ripples are 10% and voltage ripples are 1%. So, all the principles that we had studied in the DC to DC converters steady state analysis have been used in this particular example, but we have done all the calculations based on the idealized analysis. We have considered all the switches to be ideal, we have considered the inductors not to have any resistor, we have considered that the capacitors are ideal, and so on, and the non-idealities of the switches will certainly affect this, but we will see in some subsequent problems how those are to be handled. The key to the analysis of any DC to DC converter for steady state operation is just volt second balance on the inductors to find the voltage conversion ratio, volt second balance on the or ampere charge balance on the capacitors to find out the different current conversion ratios. Then the inductor voltages can be studied for the dynamic property of L di by dt is the voltage across the inductor. From that, it is possible to find out what will be the current ripple, and if current ripple is known, then we can find out what is the inductor to be used. In the same way, from the capacitors, if we know what is the voltage ripple that is allowed, it is possible to evaluate the required capacitance. So, in this particular example, under idealized modeling, we have done all the analysis to find out the voltage conversion ratio, current conversion ratio, the value of inductors and value of capacitors for 10% current ripple in the inductors and 1% voltage ripple on the capacitors. So, let us look at certain other problems. Now, this is a problem which is a non-isolated converter, and in this particular converter we will see how the non-idealities are being taken into account. Now, in this converter I have a source of Vg and a switch of S, this switch is S, and there is a freewheeling diode which is D, what you see here, and there is an inductor and a capacitor forming the filter for the converter, and power is delivered to the load which is a resistive load. in this particular example, this duty ratio is taken as 0.4 and V naught is taken to be 25 volts, and the resistance is such that the output current is 10 amperes. Okay. And the duty ratio D is 0.4 and the switching period is 20 microsecond, and the inductor used in the circuit is 20 microhenry. This is the non-isolated converter, and we wish to find out several quantities relating to the operating performance of this converter. So, we would like to find out in this particular converter what is the ripple current on the inductor, and we would like to find out what is the peak stored energy in the inductor. We will find out, let us see, delta IL, this is required to be found out. Then we would like to find out what is the peak energy stored in the inductor as the second quantity, and then we would like to find out what is the current through the switch, what kind of current will be flowing through the switch, and then finally we would like to find out the loss in the switch. Let us say these are the quantities we wish to find out. Here we would also like to take into account the non-idealities in the converter, so that we will be able to find out what is the loss that is taking place in the switch. So, what is the first thing that we wish to calculate is the ripple current. Ripple current is always found out by finding out the voltage, what is the voltage across the inductor. For example, the inductor has a voltage which is Vg minus V naught when the switch is on, and when the switch is off, it has a voltage of minus V naught, because when the switch is off, this diode is conducting and the inductor has a voltage of minus V naught during 1 minus d Ts, and then Vg minus V naught during d times Ts. So, this is the kind of voltage that is on the inductor, and you can see that during the on time inductor voltage will increase because of the positive voltage, and during the off time inductor voltage will decrease. So, we can use either the on time voltage to find out the ripple or the off time voltage. In this case, we know only the off time voltage, which is 25 volts. So, this slope is 25 divided by L, and L is given to us as 20 microhenry. So, you find that 25 volt divided by 20 microhenry is the slope of the current during the fall time, during the off time, and off time is existing for a duration of 0.6 times Ts. So, off time is 0.6 into 20, which is 12 microsecond. So, this has to be equal to delta I. So, these two units are micro. So, this will be 25 into 12, 25 into 12 divided by 20. So, that is 15 amperes. Delta I is equal to 15 amperes. So, this is the first relationship that we find out, that the current ripple in the inductor is 15 amperes. Okay. And the actual current through the inductor, DC current through the inductor is 10 amperes. So, we might now say that the DC current in the inductor is 10 amperes and the ripple current is 15. So, from 10 minus 7.5 and from 10 plus 7.5. So, this (2.5) amperes and 17.5 amperes. The maximum current on the inductor is 17.5 amperes, minimum current on the inductor is 2.5 amperes, average current on the inductor is 10 amperes and the ripple current is 15 amperes. So, this is what we have found out in the for the first part of the question, which is the ripple current in the inductor. The next measure is delta I is 15 amperes, I peak is 17.5 amperes and I minimum is 2.5 amperes. This is what we have found out. Now, what is the peak stored energy in the inductor? We know that the inductor stored energy is 1/2 of L into I square. In this example, this energy peak is 0.5 and L is 20 microhenry and the peak current is 17.5 amperes, 17.5 square, and that would be in joules. The unit for energy is joules. So, because of this micro, it will be microjoules, 0.5 into 20 into 17.5 whole square that is 30625 microjoule and that is equal to 30.63 millijoule. So, the peak energy that is stored in the inductor is half Li square and that is 30.63 millijoule. The next measure we would like to know is this, we have already found out, peak energy is 30.63 millijoule. Okay. The next thing we would like to know is what is the RMS current through the switch. We know that the current through the switch is only during the on time current is flowing, it is 2.5 to 17.5. So, this is the current that is flowing through the switch, 0 during the off time. During the on time, it first jumps to 2.5, then it linearly increases all the way to 17.5 and drops to 0 during the entire off time. So, we are now interested in finding out the RMS current of this particular current rating, current through the switch. Now, this is not a constant current, this is a variable current, it varies with respect to time. So, it is possible to evaluate the RMS current, but let us see if we can do it in a simpler way. So, this current can be considered to have two components. One is a current of 10 amperes during the on time, and on top of that a current of a ramp current of plus minus 7.5. So, the sum of these two current is what is the actual current. So, if you call this as current A, this as current B, actual current I is equal to A plus B, and one can write what we are interested in finding out I square, that is A plus B whole square, and this can be written as A square plus B square plus 2AB. Now, if you want to find out RMS, you have to find I square and take average, that is what root mean square, square it, mean it and take square root of that. So, when I square it, A square will give you the RMS of the first waveform 10 amperes RMS square, B square will give the RMS square of the second. This is the product of these two currents. If you notice this product, see this has negative area same as the positive area. So, when you multiply A and B, this 2AB's average will become 0. So, if we break up the current in this way, this term goes to 0. Because this goes to 0, my RMS consists of only the RMS of the square wave and RMS of the triangular wave. RMS of the square wave is quite easy to find out, that is simply 10 square into 0.4, because it is existing only for a duty ratio of 0.4. And the RMS of triangle is nothing but 7.5 square by 3, and then it also exists for only a duration of 0.4. So, this is a simple way of evaluating the RMS, and this current, to calculate that, so it turns out to be 10 square into 0.4 plus 7.5 square by 3 into 0.4, take square root of all that, that is 6.9 amperes. The RMS current of the switch, RMS current through the switch is 6.9 amperes. The switch itself has an on-state resistance of 20 milliohms, and it has an RMS current of 6.9 amperes. So, then what will be the loss in the switch? Loss in the switch is I RMS square multiplied by RDS on, the on-state resistance of the switch, that is 6.9 square into 20 milliohm, and that quantity is 0.95 watts. So, this is the power loss in the switch. So, in the switch, if we know the parasitic resistance of the switch, it is possible to find out how much is the power loss. Ideally, the switches do not have voltage drop, and on account of that, the switch loss will be 0. But in this particular example, if we know what is the current that is flowing through the switch, evaluating the RMS current and then multiplying with the on-state resistance will give us the loss in the switch, and similarly it is possible to find out the loss in the diode, and these two losses together will make up the total loss in the converter, and the output power plus the loss will be the input power to the converter. So, in the first example we had assumed everything to be ideal, and under that circumstance we found out applying volt second balance, ampere second balance, voltage ripple, current ripple and so on, and using that we evaluated what is the voltage conversion ratio, current conversion ratio, the value of the inductors, value of the capacitors and so on, all under the assumption that everything is ideal. In this example, considering everything to be ideal, we find out the ripple current, then we find out what is the current through the switch, and switch has a non-ideality which is the on-state resistance. By knowing the RMS current of the switch, in this particular example, we have found out what is the total loss, total power loss in the switch on an average. And in this example, we have also found out what is the peak current in the inductor, what is the energy storage requirement in the inductor and so on. Okay. The loss we have found out to be equal to 0.95 watts. This is the power loss in the switch. The diode also carries the current during the off time. If you see the off time, same 17.5 to 2.5, the average of this is 10 amperes during this time, but this is only a duty ratio of 0.6. So, you can say that I average in the diode will be 10 into 0.6, which is 6 amperes. And if the diode drop, if the voltage drop in the diode is about 1 volt, then the power loss in the diode will be 6 amperes is the average current into 1 volt, that will be 6 watts. So, we have seen that in this particular example, the diode loss is 6 times more than the switch loss. It will be so because the diode drop is about 1 volt and the device drop with a current of about 17.5 amperes and with on state resistance of only 20 milliohm, you can see that it has a voltage drop of only 0.35 volts. So, because the on state voltage of the switch is 0.35 in comparison with the on state voltage of the diode, which is 3 times less, and similarly off time is 0.6, on time is 0.4. There also diode carries current for a longer time. So, the diode loss turns out to be almost 6 times in comparison with the switch loss. Now, we will start with another problem, which is an isolated converter. Now, in this particular converter, apart from the voltage conversion ratio, inductor, capacitor, voltage ripple, current ripple and so on, we have an additional loss in the converter, which is because of the magnetizing current in the inductor. This is a forward converter. We had seen that how this forward converter has magnetizing current, which is built up during every on time, and then it is lost in the Zener diode during every off time. So, the magnetizing energy is lost in the diodes and the Zener diode, which is in the primary side of the forward converter. In this example, the source voltage is 24 volts, duty ratio as before is 0.4 and the load resistance is 1 ohm and switching period is 20 microsecond. Let us see what are all the quantities we are interested in finding out in this particular converter. Ideally, this 24 volts and a duty ratio of 0.4 and a turns ratio of 1:2/3 will produce an output voltage of 24 into 2/3 into duty ratio of 0.4 will be the ideal voltage conversion ratio, and this is 6.4 volts. Our V naught ideally is 6.4 volts. Because we do not assume that there are any losses in the switch, losses in the diode, losses in the diode. We consider everything to be ideal. In such a situation, we will find that the output voltage will be 24, which is the source voltage, multiplied by 2/3/1, which is the turns ratio of the transformer, and multiplied by the duty ratio of the main switch, which is 0.4, and the output voltage ideally is 6.4 volts, and that is what we will see at the output as the average output voltage. In a real converter, because of the several voltage drops in the converter, this V naught will not be the same as 6.4 volts. It will be a drop because of the switch, drop because of the diode and so on. For example, now we are given several information about the various drops, the parasitic resistor in the winding, parasitic resistor in the secondary winding, then the diodes which are on the secondary side, 0.8 volts in each of the diodes, and then the main active switch, which is the transistor here, has a drop of 0.4 volts, and then this inductor, output inductor, has a parasitic resistance of 15 ohms. So, all these will contribute to losses at every stage. On account of all these losses, this V naught will be less than the ideal voltage that we found out. See, ideally we found this voltage is equal to 6.4 volts. If the switch drop is 0, diode drop is 0, and then the inductor has no resistance and so on. If that is the case, output voltage will be 6.4 volts. But because of these losses which are at different stages in the power converter, our output voltage will be less than 6.4 volts. How much it will be less depends on these parasitic losses. So, it is possible to evaluate all these quantities following the same principle of volt second balance. So, what we will do is we will write the volt second balance for the entire circuit, and from that we will apply all these numbers, and we will find out eventually how much this voltage is different from 6.4 volts. For example, if you call this as Vg, Vg is the input voltage, from that there is a voltage drop Vt, which is the switch drop. This drop minus whatever is the primary current that is flowing in the inductor into R primary is the voltage drop in the primary voltage of this. So, this entire thing gets multiplied by 2 by 3, which is our N2 by N1. Now, after this voltage, after this there is one diode drop, which is this first diode drop. Then we see that after that there is a secondary current IL into RL, which is a drop in this inductor, and similarly this IL into RS is a voltage drop in the secondary, right. All these drops are contributing to that, minus V naught, which is the voltage at this point. So, this is really the voltage across the inductor during T on. So, what we notice is that now the volt second balance during on time is not simply Vg into 2 by 3 minus V naught, Vg into 2 by 3 minus V naught. Only these terms were in the ideal model, but there are several non-idealities which are now included. In the same way, if we write during the off time, you will find that 0 minus Vd, which is this drop, minus IL into RL is the drop across this, and minus V naught is the voltage at the output. And if I now multiply this by T off, this is the volt second balance during the off period. Now, the whole cycle volt second balance is that the sum of these two quantities is equal to 0. From that, we should be able to find out what is the relationship between V naught and Vg. So, we will stop here, and in the next lecture we will continue from here and then evaluate the volt second balance and find out by what amount this voltage has dropped and efficiency of the converter is affected, and so on.